Recording is rolling. It is Wednesday, August 28th. We've been spent the last few days building up to these three kinematic formulas that answer the question to your most recent lab: what equation or equations could govern the motion of the car rolling down the incline? So here are the answers to that lab. So I want to review those with you guys. Yesterday I spent a lot of class time covering these posters that are hanging around my room, PowerPoint version. So I'm going to finish that. And by the end of the class today, we'll get started on these puzzles. I gave you guys these puzzles a few days back. Okay, so finally get the ball rolling on these. Okay. And then I don't have a due date for this paper yet, but I will eventually pick this up from you guys. But I want to get that going and see how this is going to pace out first. All right, so you guys good with the agenda? All right, so let's do a little review here, a little bit of review as to these kinematic formulas. So this can describe motion for, say, if something is moving at constant speed or if it's accelerating, right? These can handle all those scenarios. Your car rolling down your incline. In fact, speaking of car rolling down incline, you guys created graphs that align with each of these. So let me get those ready to go. Got those here. So let's start with this middle formula, this middle one. So it says final velocity. So your car rolling down your incline, if you had a speed gate at the end, it was the speed it built up to, zip down, is equal to initial velocity plus acceleration times time. Okay? Now, your car rolling down the incline, what was the initial velocity if you release the car from rest? Yeah, 0. So this bit just went away. It very simply had v equals a times t. Okay? Right. Now, if you graphed on a velocity versus time axis, what shape did that graph look like? Just a straight line, wasn't it? Right? And this is it. Right? So velocity versus time, just straight line like that. Right? Ooh, are you guys ready for a critical thinking question? You guys ready? Right. What if you had not released the car from rest? I'm ready to see show hands. Show hands. Right. What if you gave the car a push? Gave the car a push. How would this graph change? Let me give you guys two options. If you give the car a push, one of these options is right and one is wrong. If you give the car a push, does this whole graph stay the same slope but just slide up here? Or does the graph stay through the origin, but the slope changes like this? Which one is correct? Show hands. How many of you guys think if you give the car a push, this velocity versus time graph, all it does is just shift straight up like this? Who thinks that? Yeah. Oh, yeah, you guys are on. Right. What? Oh, I like this class. Yes, exactly. That's right. Yeah, because now that car would have an initial velocity. You say at time 0, it's already on the move because you're giving it a push. Right? But after it gets rolling, it turns out that it picks up speed at the same rate that it did before. So it'll have the same slope as before. The slope doesn't change. I mean, it'll be going faster at every second, but the rate that it picks up speed, it happens to be the same because the gravity field acting on it is the same. All right, so there's a little extension that we hadn't talked about before. All right, let's move on to this top formula. So this is not how fast, but how far has the car moved as a function of time. The one we talked about so far is how fast is a function of time. Now we're moving up to distance. How far is the car moved as a function of time? Some of you guys had meter sticks and stopwatches, and you're saying, what's that relationship? Right? Now, again, if you release the car from rest, initial velocity could be 0. This term could go away. It should simplify to 1/2 AT squared for your car and incline lab. Right? And if you graph distance versus time, then what does that graph look like? It's a what shape? Parabola. There it is right there. X versus t, it's parabola shape, right? Because x is proportional to t squared. That always gives you a parabola, right? Now, car release from rest, 1/2 AT squared. Paul Hewitt derived that for you guys the other day. And today in class, when I go through the slides, I'll more convince you guys to, from a graphical point of view, why this is also true, right? If you had a constant velocity situation, I think we talked about this the other day. What if you're on I-95, you're just cruise control, just going constant speed? Can you guys very simply say distance equals speed times time? You guys should do that, right? And now, what if you have both? What if you have a car on an incline, so it's accelerating, but also you give it a push, right? All you have to do is add those two terms together. Later in class today, I hope by the time you guys walk out of class today, you'll be convinced that that's true, right? I'll prove this graphically, okay? So hang tight, right? And that'll be, do that. Right. Finally, these two equations so far that we just reviewed have a lot in common. They both say how much time has passed. They both possibly involve acceleration. They both possibly involve initial velocity. If you made a Venn diagram, that's a lot of overlapping variables. When we get to solving these puzzles, Sometimes you'll need something that's a little bit outside of what those offer available because they have so much in common, right? For example, what if you are not given how much time has passed and not asked how much time has passed, but you're told like speeds and distances, maybe something like that, right? Did you guys see how this third formula would be a lot more valuable to that type situation? Because it doesn't mention how much time has passed. Do you guys see that? I don't see anything about a t here. Now, there's of course time is taken along for it to have some kind of displacement at all, right? But it doesn't address that, right? So how can you show this? I think this is the least intuitive of these three formulas. And I can tell you how you get it. You can get it from a system of equations of the first two. Let me show you guys the proof for that. Between yesterday and today, I whipped up this page. Right? So I'm just very briefly going to show this to you. Of course, I'm making a recording right now. I'm going to post this recording to Google Classroom. If this really intrigues you, then stop the video at this point. Just pause the video. You can get a good look at this. Here's the first two kinematic expressions, right down here. Say, okay, so we uncovered those. Right. You can take the second one and rearrange it to solve for t time. It looks like this. This is the second, this and this are the same thing, just rearranged algebraically. Now I'm going to take this t time, I'm going to substitute it into this t up here. So that's right here. You see x equals v naught t plus 1/2 a t squared. You see that? Right. Then do a bunch of algebra. And at the end of that process, you get bing, exactly the third kinematic formula right here. Okay. Is that? All right. So that's about what I'm going to show you on that one. Okay. And then, of course, you guys also tested this in your car and car lab. Like some of you guys had speed gates for the V and also meter sticks for the distance. I think that's if you had the Hearts card, you guys had that lab, right? And if you graph V versus X, what shape did that make? There it is right there. It's a square root. It's right there. Okay. All right. You guys good on those formulas so far? There's a good review. Right. So we're back in physics. We're working on these kinematic formulas. And let's flip back over to this PowerPoint full of posters. PowerPoint poster time. Right. All right. Okay, so that's that right there. I backed up a few slides. I'm going to do a little bit of review from yesterday and then go on. Right, so you guys know that there's three kinematic formulas. Oh, you guys remember there are 5 variables that we're juggling if you're keeping track. And to solve any of these puzzles, you have to be able to identify 3 of the variables, give you guys kind of forest for the trees way of approaching these, right? Oftentimes in a physics textbook, a number will not be explicitly printed. If something starts from rest, you know, initial velocity is 0. If a car breaks to a stop, you know, final velocity is 0. Sometimes something's in free fall and you have to assume Earth gravity, right? So those are some common ones where they kind of try to hide the numbers. All right, what else we got? Oh, okay, value of G lab. I know I wrote lab on this one, but by the end of class today, guys, the end of class today, we're actually going to solve this problem, but for an alien planet. Suppose you're hopping around the galaxy, you know, like landing on different planets, right? Do you guys think, here, in principle, I want you guys to see this is true, and later on today, we'll solve this, right? Suppose you come across some cliff, and you reach out and you drop a ball. You guys drop a ball. What do you know about initial velocity? 0. Okay, so bing, there's a kinematic variable. We know one. Hey, what if you measure the height of the cliff? Bing, there's a second kinematic variable, displacement, right? And what if somebody brought a stopwatch on this trip? And we say, how much time does it take for the ball to hit the ground? Bing, is that 3 kinematic variables right there, right? Do you think in principle you could solve for the gravity field that would make all those align? You could, couldn't you? Yeah, we'll do that. Okay. Right. And furthermore, you could solve for the crash speed. We'll also do that later today. Okay? So hang tight for that. You're going to see all this today. You guys remember this yesterday? This is in your notes because I had you guys draw that table and I uncovered one cell at a time. We did the whole table like this. All right, so quick review. The edge of a cliff, drop a ball. Every second you take a picture. See how the ball's like spreading out every second? Now let's make a table full of values. We got time in seconds, 1 second at a time, 0, 1, 2, 3, 4, 5. Acceleration meters per second squared. Hey, look, it's the same acceleration all the way down. Acceleration is constant. It's all falling in the same gravity field, isn't it? Right. Now, speed is increasing, but notice the speed or velocity is increasing at a constant rate, right? It picks up 10 meters per second per passing second. Hey, look at that. 0, 10, 20, 30, 40, 50. You guys know all these columns are, of course, related to each other, right? Did I mention the other day they have calculus type relationships, right? Yeah, right. We're really doing integrals is what we're doing, right? So hold on to that word. See that one day. right? And finally, how far has the ball fallen? Now, this last column was maybe the trickiest to figure out. Could that be that kinematic formula that goes something like 1/2 AT squared? Like the distance fallen could be 1/2 AT squared if it starts from rest, right? So see if you guys remember this. Guys, go to the edge of any cliff on Earth. Go to the Grand Canyon. Reach out. Drop a ball. How far will that ball fall in 1 second? 5 meters. 5 meters. Yeah. Right. So it falls 5 meters, and the speed it would pick up to would be 10 meters per second. Ah, that's right there. Right. How about this? Go to the edge of how about you go into a cave and you see a mine shaft. You can't see the bottom, so you drop a rock and you count to 5. It takes 5 seconds for that rock to hit the bottom. How deep is that mine shaft? It's about 125 meters deep. How'd you know that? College. It's also 1/2 AT squared. You just plug in 5 seconds. You guys remember all that? All right, we're doing a little review here. We did all that yesterday. All right, and here's the graph. I think this is actually the last slide you guys saw yesterday. All right, so let's see this one again. All right, so you guys see this table and these graphs are the same story, just from different points of view, right? You got more equation based and maybe more graph looking, right? But the same story. And these graphs are related to each other. So if you know one of these graphs, you can kind of figure out what the other two look like. Right? So go to the edge of a cliff, drop a ball. I usually start with this middle graph here. Drop a ball, inertial velocity is 0, but then it's going to pick up speed, but at a constant rate, right? Oh, guys, what is the rate change of velocity called? What is that? Rate change of velocity. Acceleration, exactly, acceleration. And if it happens to be free fall, it's acceleration due to gravity. I usually call that g, right? Guys, and the slope of v versus t, acceleration, that's therefore the coordinate of a versus t. Ah, I see a constant slope on v versus t. That's the coordinate of a versus t. It's the same thing. You see it? Right? Oh, that v versus t graph is a really information-rich graph. You guys see, not only can you see velocities, because those are all the individual coordinates, right, that the line is sweeping through. The slope represents the acceleration, right? And the area under the curve represents displacement. I'm about to get to talking about that too, right? If you're ever not sure what property of a graph represents what, because it could be so much information packed into a graph, look at the axes and you can kind of figure out the answer. Like the slope example. Guys, is slope rise over run? That's what slope is, rise over run. Let's carry the units into exactly that expression. Because what is meters per second per passing second? What is that? That's meters per second squared, which describes an acceleration, doesn't it? Right. You could also go the other way. So guys, what is speed times time? What is that? What is speed times time? Is that distance, right? Let me go back. Let's go back. Bing, right there. Now, this one showed a constant speed. Isn't it true if you have a constant speed like cruise control? It's very simply speed times time is how far you go. 60 miles an hour for 1 hour. Oh, I just want 60 miles. I got that? Right. But what if it wasn't a constant speed? What if you do something crazy like you hit gas pedal, brake, and you got some like crazy Dr. Seuss looking curve? Is the area under v versus t, does that still represent how far the car went? It sure does. So let's go forward. Forward, bing. All right, now we're back here. Right. So do you guys see a green triangle right there? That could still represent the displacement, how far the ball fell, right? But you guys see as time opens up, you're going to start with a little tiny triangle down here, and then it opens up bigger. So the triangle is going to increase like a parabolic relationship. So x versus t looks like a parabola. Look at that. You see it? Okay. And then, what do I say here? Oh, and look at the units. The units can tell you that too. Meters per second multiplied by seconds brings you back to meters, right? I think the one relationship I have not mentioned is this one right here, going from x to v. Guys, what is the rate change of position? That's a very fancy way of saying what? Rate change of your position is also called your speed or velocity, right? Rate change of my velocity, rate change of my position. That's velocity, right? That's to say, on a graph, the slope of x versus t tells you your instantaneous velocities. Now, if you hold a ruler flush to this parabola-looking curve, well, it has all different slopes depending on where you put your ruler flush to the curve, all different slopes. Right? And I labeled those V1, V2, V3, V4, V5. Right? V is in velocity, right? Okay, so the velocity is constantly increasing, but it's just increasing at a, turns out to be a constant rate. If you took all those slopes of x versus t and you plotted them, like I see zero slope there, then a shallow slope, then a steeper slope, then a really steep slope. Right? If I plot those as coordinates, they'll all line up in a straight line on a v versus t graph. I see that too, right? Right. And then, yeah, you guys remember that whole conversation is all calculus. That's all what calculus is, right? First half of calculus is rates of change. That's these red arrows here. Second half of calculus is that whole process backwards. That's these green arrows here, right? So if you're in calculus and one day your teacher teaches you derivatives, a derivative is just a rate change equation. Take some of these physics equations, take the derivative of them, the rate change when eventually you did that in a calculus class, and you'll see that it all aligns. It's all, right? It tells you like the rate change of position versus time tells you velocity versus time. The equations match exactly. Okay? All right. All right. Here's new stuff. All right. Let's do a step more complicated. So we're at the edge of a cliff, but this time I'm not going to drop the ball. This time I'm going to throw it. No, I'm not going to throw it to the side yet. We're not ready for that yet. I'm either going to throw it straight up or straight down. So you see here, I'm at the edge of this cliff in the middle of the page. I can either throw this ball straight up or I can throw it straight down. So it's still linear motion, right? Straight up and down, right? If I had more time, you know what would be a better way to show this is to give you guys blank axes and have you guys do these graphs from scratch. But I'm just going to do this way. Just follow me on this. I want you guys to see that this kind of makes sense, right? Why these graphs would look the way they do, right? So let's start with throwing a ball upward. So edge of a cliff, I'm going to throw the ball straight up, right? Now, remember yesterday I was defining down as the positive direction. Let's go ahead and keep that convention. So down is still positive, which means if I throw the ball straight upward, I'm throwing it which way? Positive or negative? Negative, right? So could you say it has a negative initial velocity? Hey, look at this V versus T graph. Look at that. It has a negative initial velocity right there, right? Also, if I throw it straight up, isn't it true it's going to peak at some point and it's going to fall back down because gravity is eventually going to win, right? Oh, and guys, at the point that it peaks, what do you know about its speed at the very top? Zero. It has zero speed at the top. Now, that's only true for one instant, but it's not moving quite up or down at that instant. Hey, go back to the graph. That's like zero. Hey, zero speed. Wouldn't that be at the very top? It has zero speed at the top, right? How about the slope of this V versus T line? Guys, what is that slope of that line equal to? The what property? What is the rate change of your velocity called? Starts with an A. Acceleration. Hey, oh, there's the acceleration versus time graph right there. You guys see that? Right. You guys see the slope of V versus T just is the gravity field G, right? Hey, is that true? Like as soon as you release the ball, you threw the ball. It's moving really fast, right? As soon as the ball leaves your hand, is it just accelerating the same as gravity, right? Right. All right. So the acceleration can be independent of the velocity. Finally, let's do x versus t. I usually save x versus t for the end because it's the most complicated looking graph. Right? Okay. Again, defining the top of the cliff as 0.0, just like we did yesterday. Right? If I throw it upward, I'm throwing that into negative territory. So the ball starts heading into negative territory, but look, it's like slowing down. Now it will peak. There will be some maximum height. So that graph's going to max out, I guess in this case, in the negative territory before it bends back around. And look at there, guys. Look at that vertex of that. Ooh, guys, what shape is this again? What shape is this? Parabola. The vertex of that parabola. Look at when it aligns with the bing, with the zero velocity point on the V versus T curve. You guys see those two graphs align right there? Right? That's a really good tidbit to know in this class, because I might ask you a question like, you throw a ball straight up, how high does it go? And to answer that question, first you have to figure out what time it reaches the maximum height. So, well, I can set the speed equal to 0. Then I can solve for the time. Then I can plug that time into my distance equation. And then I can figure out how high it goes. Okay, something like that. Just give you guys a forest for the trees kind of roadmap to thinking about these things. Okay. All right, guys good there? All right, let's switch over to throw a ball downward. You guys ready to throw a ball downward? Okay, so go to the edge of the cliff, but this time I'm going to chuck the ball straight down, which means I'm throwing it into the positive direction, right? Which means it has a positive initial velocity. Do you see it right there? Bing, positive initial velocity. Now, after I release it, does gravity pull it down faster, faster, faster? So it's speeding up. Does it speed up at the rate of the gravity field? Okay. All right. And then, okay, so this acceleration graph looks, okay, is also a constant value, right? Ooh, guys, is this acceleration graph on the right exactly identical to this acceleration graph on the left? Are those the same? Yeah. Now, this ball on the left is going up. This ball on the right is going down. But they're both under free fall, so they're both accelerating the same. That doesn't mean that they have the same velocity at every time. That doesn't mean that they have the same height at every time. but they are accelerating the same. Okay, same gravity field. Okay. How about let's go back to the v versus t graph. Here, I'm going to hold my meter stick up to the projection here. Is this slope on the v versus t equal to this slope on this v versus t? Are those slopes the same? Yep, they sure are, because they're both equal to g. On Earth, that would be about 10 meters per second squared, right? That'd be true, right? And finally, the last graph I haven't talked about yet, this one on the top right. Okay, so x versus t. Or so I'm calling the top of the cliff 0.0. That's the origin 0.00, right? I'm chucking the ball straight down, right? Ooh, it looks like this graph does curve a little bit. There's a little bit of a bend to it. Hey, what shape do you think this curvy looking graph is a part of? That's a part of a what shape? Parabola. That is a piece of a parabola, isn't it? It's a little sneaky. It's like it's out on the tail of a parabola, isn't it? Right? It sure would be. Right? You guys see that too? Right, you guys good with those graphs? Right, great. Okay. Now the next slide coming up is, I'll tell you what it is. You guys see this graph on the right, the v versus t graph on the right? Right. I'm gonna blow that graph up big. You guys ready to blow this graph up? Now it's big. You guys see? Same thing? Right. And okay, so we got velocity versus time for, I just chucked the ball straight down from the edge of the cliff, right? And what I could just, oh, look at this velocity equation. Does this look like y equals mx plus b? It sure does, right? Oh, where else have you seen this? Vf equals v naught plus at. Where does that look familiar from? Is that your second kinematic equation going on right here? That's what that one is right there, isn't it? You see that? Right? So the speed it picks up to is however fast you throw it plus acceleration times time. Right? So let's get back to the slide, right? Because I want to do more with this. Right? All right. So okay. So you guys good so far? Right. Now, guys, tell me again. What does the area under a v versus t curve represent? And if you're not sure, then let's figure it out from the units on the axes. Right? Could area be something to do with base times height? Something to do with base times height? Like if I forgot to ask you guys that. The rate change of velocity, of course, is acceleration. Right? Forgot that. Velocity versus time. Right? What if I split this up a little bit? Guys, this speed times time, what is speed times time equal to? Distance. And that's also true with the units. If I do meters per second times seconds, the seconds cancel out, it leaves you with meters, which describes the distance. Okay. So here's what I want to do is I want to, let's see what the distance would be, right? And this is going to lead somewhere interesting. Okay? So we do. Do you guys see a triangle sitting on top of a rectangle? You guys see that? Let's figure out what are the areas of each of those individually. So guys, what is the area of this rectangle? What is that? Yeah, base times height, which is some time it's been going for, times the throwing speed, wouldn't it be? Is that v naught t? That would be, right? Now, how about this triangle? Now, this triangle's a little trickier. I want to bring that off screen here. Let me flip over here. Come on, stop share. Right, here we go. I'm gonna flash up some notes from earlier today. So I cover this a little bit of time, right? So there's just the triangle. You guys see I just simplified this down to just looking at the triangle as if you'd released it from rest. So we got that, just the triangle. And I'm making the claim. Okay, so there's the equation. The speed it picks up to is a times t. Right? A times t. I'm making the claim that the area between the curve and the time axis represents how far it went, x. Right? Oh, guys, what is the area of a triangle equal to in general? Area of a triangle equals 1/2 base height, exactly. And the base in this case is equal to however much time it was moving. And the height is equal to what? The final velocity, which is also equal to a times t, right? As long as it starts from rest kind of thing, right? So let's put it all together. So here we go. The distance it moves then is equal to 1/2 times base times height. Hey, can I combine these two times? Right? Could that give me 1/2 at squared? 1/2 at squared? Where have you guys seen that? Wasn't that also your car and incline lab? Something like that, right? Also, that looks like this right here. You guys see what we just did? We just graphically derived this entire thing because this paper shows this bit right here. this is the triangle that was sitting up. Remember on the when it flipped back to the PowerPoint, this was sitting on top of a rectangle. The rectangle, that was that guy right there. Tag them together. There's the rectangle plus the triangle. Ooh, you guys see that? You see that? Ah, we just derived that one graphically. There you go. So slip back over PowerPoint. All right, so then fill this in. Bing. There's your V naught t. There's your 1/2 at squared. Put it together. You get how far it went. Right now you guys can solve any of these. All right. This one. Okay. I don't want to do this activity today, but pretty soon. One of these days coming up pretty soon, we'll do this one. What if I set you up with a partner and say your partner drops the ruler and you catch it as fast as you can? Now, isn't there going to be a time delay between your partner releasing the ruler and you catching it, right? Ooh, guys, think about this. Guys, there's some time delay between reality happening in the world and your brain processing it. Suppose you're driving in a car. A deer steps out in front of you. Do you think it takes a tiny split fraction of a second before you can slam on the brake? Yeah, I wonder how much time that is. Right? There's some human reaction time. Probably slower than a fly. It's kind of hard to swat a fly. Wonder how fast that is, right? Well, last few days, one of the problems we've really been focusing on is you go to the edge of a cliff, drop a ball. If you know how much time has passed, you can in principle figure out how far it fell. About 125 meters deep. How'd you know that? College. That's that one. Do you guys think you could turn that around? If you know how far something fell, you can back calculate how long it was falling for. Ooh. All right. So yeah, today I just want to introduce that idea. Have you guys sleep on that for a day? See if you guys can figure this out one of these days coming up pretty soon. Okay. Right. You guys think you can? All right. Yeah. So we'll save this one for pretty soon. This will be coming up. We'll do this one. Okay. All right. Okay. This one. You guys got your notes out. Yeah. All right. See, everybody's got notes out. And of course, I got paper on these stools if you ever need some paper. All right, so let's do new graphs. So here's a scenario. Car brakes to a stop. And oh, look, it's the same old set of axes over and over again. Got X versus T, V versus T, A versus T. I'm gonna, okay, so you guys are getting those axes drawn in your notes. Right? So yeah, we'll do this one traditional like I prefer to do it, which is, can you figure out what those graphs look like before I show you on the presentation what they look like? Because like always, if you can figure it out before I show you, that's a good indication that you know how to think about these problems, right? How to solve them. Like, for sure, you're going to get these right. Okay. Let me add a word to the title. Let's say the car brakes uniformly to a stop. Physics textbooks will throw in that word. They'll say the car brakes uniformly to a stop. That just means constant acceleration. So it's going to slow down, but at a constant rate. Okay, something like that. Right, yeah. So this one's a new scenario. All right, walk around, check your guys' notebooks. All right, who's gonna get these graphs? Okay. Right, so the car's driving along, and then say the driver slams the brake. And as soon as he starts slamming the brake, then we're gonna start drawing the graph. So that'll be time 0. You start slamming the brake at time 0. All right, who's gonna get these graphs? Who's gonna get these graphs? Ooh, all right. Elise got the V versus T. Yeah, that one's right. Zachary got the V versus T. Who else is gonna get these graphs? Ooh, close. Maybe it's a missing uniform. Yeah, I remember. For accelerating scenarios, the X versus T tends to be what shape, and the V versus T tends to be what shape, and the A versus T tends to be what shape. You look back in your notes last few days, right? The same basic shapes are going to carry over. Of course, it's a new scenario, a little different. All right, yeah, Peyton got the V versus T. Ian got the V versus T. Yeah, Isabel got the V versus T. Oh yeah, Elise got all of them. All right, first all the winner. All right, and Yeah, Olivia got all of them. All right, all of them. All right, Alexander got the V versus T. Zachary got the V versus T. Ooh, yeah. All right, Luciana got the V versus T. All right, pretty good. All right, yeah, you guys are getting these. If I gave you guys some more time, you'd be getting those too. All right, so let's go over the answer. Yeah, some of you guys getting these. So yeah, let's start with the V versus T. I usually start with anyway. So the curve breaks to a stop. It had to have been moving at the beginning of the interval. So it does have an initial velocity. That would be true, right? Right. If it breaks to a stop, what do you guys know about final velocity? Final velocity would have to be 0. So after some time, it has 0 velocity, right? And if I threw in the word uniformly, breaks uniformly to a stop, that would tell you that it would be a straight line that connects those 2 points, right? Actually, in this class, you can assume that's going to be the case, right? It's always going to be straight lines for your V versus T, okay? Thanks for that. All right, so there's one graph down. Okay. This graph has some properties. Right. Remember, guys, that V versus T graph is really information rich. Not only does it like time point for time point tell you the velocity day time point, right? But also the slope represents the acceleration, the rate the car is slowing down, and the area under the curve tells you how much road the car took to stop, what distance, what braking distance, right? It's all embedded in that one graph. All that information is. Right. All right. Let's see. I think the next graph I have queued up is this top right one. Guys, position versus time. This is the trickiest one. I think a couple of you guys got this. Right here, how about this? Let me, before you guys see the answer, help you guys out a bit. You guys see this green triangle tells you how far it took the car to brake? Right. What if I split that? Suppose it took 3 seconds for the car to stop. You guys see it takes tick, tick, tick. Can you guys imagine 3 seconds to come to a stop? Right. Now, during the first second, do you guys see a big old trapezoid right here? Big old trapezoid? That represents a lot of road, a lot of road. During the next second, do you guys see maybe a smaller type trapezoid? Okay, so the car's still moving forward, but just not as much road. And you guys see during this last second, here it comes to stop, a little tiny triangle right there, little tiny triangle. This car's, again, still moving forward, but only a tiny bit. Now, if you plot that on an X versus T, it's going to look like, bing, that right there. Okay, so I'm going to define a pump and the brake as 0.0. Right? Then during the first second, the car went a long way. During the next second, yeah, it's still moving forward, but not as much. And during the very last second, it's coming into stop, still moving forward again, just a tiny, tiny bit. Right? You guys, what shape is that right there? That's a parabola. Where's the vertex of that parabola? Up here at the stop point, right at the end. There's the vertex. You guys see that? So right there. Right, guys good? That was the probably trickiest graph that you guys have seen so far. Right? And some of you guys got that, which is awesome. Right? All right, last graph. Let's do acceleration versus time. What does that look like? How about this? Do you guys see a constant negative slope on V versus T? Is that going to translate to a constant negative coordinate on A versus T? Bing! There it is, just like that, just like that. There you go. All right, guys good? All right, ready for next slide? Next slide. All right, here we go. Oh, okay, and there's some other properties. But guys, so all that red ink is the instantaneous rate change. All the green is like the accumulation, right? The calculus terms are derivative and integral, if you see those in a calc class one day. All right, here's the last slide I got for you guys today, and then we'll go start solving some puzzles. All right, so last slide today is, okay, so one property we're dealing with is called velocity. A different type property is acceleration. That's the rate change of velocity, right? And since these are vector values, they could be either positive or negative. So what if you have different combinations of velocity and acceleration, right? And okay, we can make this into quadrants, right? Like, you know, positive, right? So here, guys, which of these properties, velocity or acceleration, do you think tells you your direction of motion? Like whether you're moving forward or backward? Let me see, show of hands. How many guys think that velocity tells you your direction of motion? Who thinks it's velocity? Velocity. Yeah. All right, winner. Yeah. So if you have a positive velocity, let's call that moving forward. If you have a negative velocity, let's call that moving backward. Is that okay? These scenarios, let's call this all, you're in a car, right? So if you have a positive velocity in the car, you're moving forward. If you have a negative velocity in the car, you're in reverse going backward. Okay? All right. What if we combine that with an acceleration, which means that velocity is now going to be changing? which means you're going to be either speeding up or slowing down. And that's what I want you to figure out for each of these quadrants. Right. So first quadrant, positive, positive. What if you have a positive velocity and also a positive acceleration? That means you're doing what in your car? You're moving forward and also doing what? Speeding up. Exactly. That's exactly what I'm looking for. Bing, right there. Moving forward, speeding up. Okay. Right. So yeah, not only you're moving forward, positive velocity, but you have positive acceleration. Yeah, you're moving forward faster and faster. Ooh. Next quadrant. Let's do the bottom right one. Negative, negative. Right. So because by itself, negative velocity means you're doing what in the car? Moving backward. Right. So you're in reverse. Right. Right. Now, if you combine that also with a negative acceleration, notice this, the same direction. So you're moving negative, but you're also accelerating negative. That means you're moving backward. How? Speeding up or slowing down? How about that one right there? Speeding up. Right. So here's the big picture takeaway. If velocity and acceleration have the same sign, it's always speeding up. If it's positive, positive, you're speeding up forward. If it's negative, negative, you're speeding up backward. Something like that. So as you're either crafting equations or interpreting equations out of a book, right? See something like that, right? Right. You guys good so far? Right. Now let's see if the signs mismatch. What would that mean? Let's do this bottom left quadrant. What if you have positive velocity, so I'm moving forward, but also negative acceleration? What do you think that means you're doing? You're moving forward and who knows? Moving forward and slowing down. Bing, right there. In fact, back. Hey, that's that one right there. You guys just did that one. That's what we just did on the last slide. Moving forward, slow into a stop. Right, forward. Bing. All right, so now we're back up to, that's what we just did, right? You guys just drew those three graphs a few minutes back. Right, right. And last quadrant, what if you have a negative velocity, but a positive acceleration? What would that mean? You're moving how? Right. Well, yeah, backwards, right? Backwards, because negative velocity, but also you're moving backwards and also doing what? Slow into a stop. Bing, right there. Moving backwards, slow into a stop. There you go. So, okay, so then the takeaway is if the signs mismatch, if velocity and acceleration have opposite signs, that's always a slowing down situation. All right. Did I think I put that one in your thumbnail notes too, didn't I? I think it is. Let me check over here. Oh, no, okay, whoops, I guess it missed the cut. Oops, all right. Well, you can always download this presentation too, right? So you got that too? Right. Okay. All right. All right, you guys ready to solve some puzzles? Solve some puzzles. Okay, let me get this back in here and then we're gonna solve some puzzle time. All right, let me get my puzzles ready. You guys remember I gave you guys that page with the boxes on it. So I'm gonna do that page with the boxes. All right, so flip my screen here. All right, here we go. Linear motion. All right. So big picture, there are 10 different scenarios here. Now, you guys remember there are 5 kinematic variables, and you have to have 3 to solve the other 2. If you think about probability combinations, that means there can only be kind of 10 scenarios. So kind of every single formula-based question I could ask is on this page, right? Related to linear motion. Right? All right, so I circled some of these that I would like to do in class today before the bell. So we'll see if we can get that far, but we'll see. Right. So first one, number 1 and 2 apply to this first scenario. Right, you guys got? Oh, also a little bit more about this page. You guys see I gave you guys these very convenient boxes that very explicitly mark what variables you have, like time, acceleration, displacement, initial and final velocity. Right. Traditionally in a physics textbook, they won't be that explicit with it. So they'll give you like some little paragraph list, and you kind of have to figure that out. Helping you guys out a little bit here. And so first scenario, which is number 1 and number 2, right? A baseball is thrown from the pitcher's mound, travels towards the plate at approximately constant velocity, right? Maybe that's not strictly exactly true, but it's pretty close. Right? If you're up in a blimp watching the ball go across the field, it's pretty much constant velocity. So we're going to say this. Calculate how much time did it take to reach the plate? Like, what's the batter's reaction time? And also, hey, I wonder what is the speed that it was crossing the plate. So let's figure out that. So gonna back up here. Right. Oh, I should say your numbers are probably different than my numbers. I'm eventually gonna pick this up and score this for you guys, but I don't have an exact due date on this yet, but in time. So number 1 and 2, I'll do with you guys here. And again, my numbers are probably different than your numbers, but we all have the same scenarios. So here's the mound, here's the plate, okay. And I did give you guys the distance because there's a regulation distance, so I pop that in here. Okay, so from the mound to the plate, let's call this distance x equals 18.4 meters. I think that should be the same for everybody. Right? That's got 18.4 meters. Right? What else I give you? I gave you the throwing, the pitch speed, initial velocity. So let's get a baseball going. Right. Initial velocity. Now my paper says 37 meters per second. Right. But careful, on your paper, it probably says something different. Okay. I also said constant acceleration, or sorry, constant velocity, which means 0 acceleration. So I'm going to write that too. I'll say acceleration is 0 meters per second squared. So basically, the ball's not speeding up or slowing down. It's just pretty much constant velocity. Okay. So again, from our point of view in the blimp, looking down on this. Okay. All right, guys, get them set up. And the questions are, what is the reaction time of the batter? And what speed is the ball crossing the plate? Zip, zip. All right, guys, get the premise. Okay. Now, for all the puzzles on this page, well, okay, there. You can go equation shopping, sort of. So, hey, here's these 3 kinematic formulas that can handle questions on that page. So, you guys tell me which one do you want to start with? The first, second, or third? Yeah, let's just pick one and play with it. Let's say you pick the second one. Let's say you pick the second one. Right, I had that nominated last class. Right? Let's go. Final velocity equals initial velocity plus acceleration times time. Right? Maybe pick that one. Right? Sometimes you pick a formula and it works, and sometimes you pick one and it doesn't work. And sometimes there's multiple ways to start a puzzle. So sometimes multiple work. Right, so what do I know? What do I not know? I know this number is 37 meters per second. I'm trying to solve for the final velocity. What's the speed the ball crosses the plate? Right? And ooh, hang on a minute. Isn't acceleration 0 meters per second squared? What happens to this term? It goes away. It's gone. Oh, is that the answer right there to number 2? That's number 2 right there, isn't it? Right? Which of course it is. Maybe some of you guys figured that out before I even wrote anything down. Because whatever the pitch speed is, if there's no change in velocity, of course it's going to be the same all the way across, including when it crosses the plate. Right? There's number 2 right there. Right, everybody got number 2? Guys good? All right, let's go answer number 1. Now, number 1 says, how much time does the batter have to react? Okay, so we need something with time in it. Well, I guess it's not the one that we already did because that didn't really be able to answer how much time. Okay. Maybe we need to bring in distance somehow. Guys, which is the only kinematic formula that has both distance and time in it? The first one. Yeah, the first one has an x and a t. That's the only one that has both the x and the t. Well, let's play around with that one. Let's see what happens. So I'm going to go x equals v naught t plus half at squared. But wait a minute. What was acceleration again? 0, because constant velocity. That term just goes away. Oh, you know what? This is probably even simpler than all that crazy stuff. Look, it's just it simplifies to just distance equals speed times time. Right? Because anytime you have constant velocity, that's really all you need. Maybe I kind of over-explain that point, but that's all you need. Distance equals speed times time, right? For 0 acceleration. Okay, so I know this is, yeah, I'm going to a little fancy. I'm going to split my paper. And then I could, x equals v naught t. I could solve it in terms of variables. I could also solve it plugging the numbers in first. 18.4 meters equals 37 meters per second multiplied by how much time. Okay. Right, so in terms of variables, all I have to do is divide down the speed. Actually, you could drop the subscript not if you wanted to be that. Okay. In terms of numbers, it's the same story, just with the numbers plugged in. Be 18.4 meters divided by 37 meters per second. The meters goes away. 1 divided by 1 over seconds gives you seconds. Looking at the reaction time is 0.497. I can round that to 0.50 seconds. There's the answer. And that's the answer to number 1. So number 1. Okay, you guys got a reaction time for your batter? Again, right back up here. Anytime you have a constant velocity scenario, you're really only dealing with this equation here, distance equals v times time, right? I guess breaking out this whole poster is a little bit overkill, but I wanted you guys to see that it would be consistent, okay? But all these other ones, really, we need the poster for. Right. You guys ready for our next scenario? Right. Let's do number 7 and number 8. Number 7 and 8 down here. Right. Zoom in here. I got focus here. My camera's got to focus. Here we go. A ball is dropped off a cliff of given height on an alien planet. Ooh, spooky. Hey, alien planet. Do you guys think maybe we don't know what is the gravity field right away? I might have you solve for that. Okay. Do you guys remember the slide sort of on the PowerPoint talking about this one? Here it is. Making good on my promises. It takes the given time for the ball to reach the ground. Find what is the gravity field of the planet, and what is the speed the ball crashes into the ground. Ooh. Okay. So look what we got here. We know the height of the cliff. There's the height of the cliff in meters. Guys, the fact that you dropped the ball. Guys, what does drop tell you again in physics? Yeah, 0 initial velocity. Yeah. So I did explicitly print that number. A traditional textbook would not. You have to figure that out, right? And then somebody brought a stopwatch, and we know it's 3 seconds for all that to happen. So solve this one. So this is number 7 and 8. 7 and 8. Okay. I'll draw a little picture here. Here's a cliff. Visualize this. We got a ball. Okay. I know the cliff height. I'll call it h equals, or you can say x if you like, but use h. Right, my cliff is 19 meters. 19 meters. And yours is probably something different. Oh, let's zoom out over there. Okay. The fact that I dropped the ball, I know initial velocity was, of course, 0 meters per second. Okay. But then this ball is going to crash going at some final velocity that we can solve. Okay, so somebody brought a stopwatch and says the time it takes. All right, let me see. My paper says it took 3 seconds. 3 seconds. Okay. And along the way, we'll be able to determine what is the gravity field. So what is the gravity field? What is the final velocity? Is what we're solving for. Okay, so you guys give it the setup? All right, let's go equation shopping. Which equation do you guys want to kickstart the solution? First, second, or third? Okay, I see some nominations for number 2. Let's see number 2. See if we can do that. Okay. See. Well, okay. What did we know or not know? I know V naught 0, right? So that goes away. Right. Okay. I don't know the gravity field of the planet, and I also don't know the crash speed. Guys, if you have one equation with 2 unknowns, is that solvable by itself? Not by itself, right? Maybe in a larger system. Guys, can you have one equation with 1 unknown? You can solve that. How about 2 equations with 2 unknowns? Is that solvable? How about 3 equations with 3 unknowns? Is that solvable? Yeah. So all those would be. But if I have 1 equation with 2 unknowns, not quite. So let's pick a different one. If you pick a wrong one, you'll just run into that problem. You can just go back and pick a different one. And so what's another nomination? Number 1? Number 1? Ooh, maybe I like that one. Because I do remember I measured the height of the cliff, and somebody also brought a stopwatch. Hey, that's a good nomination. Let's try that one out. Let's see that. Let's go. X equals V naught t plus half a t squared. Okay, would you like that? Oh, but wait a minute. What was my V naught again? 0, because we just dropped the ball. so I can simplify this. I'm going to change my terminology a little bit. The general displacement, I'm going to replace with h for height. Right? I'm going to get rid of the v naught t because that's just 0. Right? 0, whatever. Right? And then in place of acceleration, I'm going to do g for acceleration due to gravity. It'd be like that. Just like that. Okay. Is that all right? So I changed my terminology a little bit. Okay. Right. Here's where I'm going to split my paper and solve this 2 different ways. I can do in terms of variables. So h equals 1/2 gt squared. Right. Ooh, hey, is that the college equation? That's college, isn't it? Isn't that college right there? Right. It's about 125 meters deep. How'd you know that? College? And or I could plug in the numbers first. So I could go 19 meters is 1/2 times gravity field times 3 seconds things squared. Right. So I can solve in terms of variables, or I could solve plugging the numbers in first. Right. If I solve in terms of variables, cross multiply the 2 and divide it on the t squared. So the 2h divided by t squared. Yeah, my AP students especially, I encourage them to get used to solve in terms of variables. Right. But my other class, like, if you want to plug in numbers first, that's all right. Right. So in terms of numbers, it's the same process though, right? Cross multiply the 2 and divide by the time squared. So in this case, it's going to look like 2 times 19 meters divided by 3 seconds being squared. Right, that's my gravity field. Now let's get a number on that. Yeah, let's do 2 times 19 divided by 3 squared. Okay. Now, before I hit enter, a really good practice in this class physics is before you go plugging and chugging, reason out in your mind what might be a reasonable answer. Do you guys remember if this cliff was on Earth, that the ball falls 45 meters in 3 seconds? Do you guys remember that? That big old table we did yesterday? But on my alien planet, in the same time, it only fell 19 meters. That's a lot less. Guys, if it only falls a short distance in some time, do I have a really strong or a really weak gravity field? It must be really weak, which means it must be less than 10 meters per second squared. So I hope this number reflects that. It does. 4.2 meters per second squared is the gravity field on my alien planet. All right, guys got that? All right. And one more thing I'll do with you guys for the bell is, what is the crash speed? Let's do this. Crash speed could be equal to, can I do v naught plus gt? I could do that, right? That'd be one way. Goes away, whatever. So the crash speed, or you could pick the third kinematic equation, play off the height of the cliff. You could do that too. Let's do 4.2 meters per second squared for 3 seconds. It was 3 seconds, right? Yeah, 3 seconds. Okay. So times 3, I'm getting the crash speed is 12.7, it rounds to, meters per second. Of course, all these numbers have units. If you're doing it right, you should be getting the multiple choice answers. All right. You guys good? All right. So yeah, I think this is going to be our main focus tomorrow. Right? If you guys bring in this puzzle page, and we'll do more puzzles. We'll continue this adventure tomorrow.